I'm from Idaho.
Where are you born?
It was a long time ago, so I don't remember. Yeah, I was born in Eastern Europe, Bulgaria.
Teachers class.
It's what?
So one day you just teach a class in Bulgarian.
Oh, you want today's class to be in Bulgarian? I can do that.
I think right now.
Is it going to make any difference? Thanks. Okay, time to start. And so the homework assignment is due tonight. And we have one more homework assignment due on Friday. The chapters are simple. There is a lot of writing in them, many words, but what you need is the substance there, and the substance are statements without proof, because we're not in a position to prove any result from quantum mechanics or relativity. So you need to understand what the formulas that they give you, what is their conceptual meaning, but the arithmetic there is not like the challenge at all. So good example of what type of questions you're going to have on the final exam from the new material is the homework assignment. No more. Just understand the questions in the homework assignment for the last several chapters, the assignments, and you're going to do very well on the new material. For the old material, on Friday, I'll give you a short list of calculational problems that you have to review, because you cannot keep in your mind all the material that we covered during the semester. So you're not going to get exactly the same questions, but if you understand the questions from those old problems, you're going to have some version of that. And most importantly, conceptual questions, all conceptual questions are fair game. So you're going to see conceptual questions from all over the So review them, again, understand them conceptually rather than trying to memorize answers. And on Friday, I'm also going to give a formula to calculate the final grade. Just make sure that your learning points are entered in the Google Doc. And everything is going to be fine. So the final exam is scheduled for this section. It is scheduled on Monday. This coming week on Monday at 12:30. If you show up at noon or shortly after 12 o'clock, and if this room is not occupied by some other exam, some other people, you can start working early. But we have to finish at 2 o'clock also. Okay. And again, the exam questions are going to be, you can, if you know the material, you can finish in something like 20 minutes. So, okay. So let's see what is this problem number 5. Problem number 5. Okay, so here's the problem. So problem number 5 is about hydrogen atom. Material that you have covered in general chemistry class, And I'm sure that in that class you also got a bunch of formulas without proof. So you don't need to memorize here any formulas because all formulas that are needed are provided. But you need to know which formula is for what. And so you have a hydrogen atom. They give you the principal quantum number for this electron in a hydrogen atom. So for my version, the principal quantum number is 4. This means that the hydrogen atom, the electron is in highly excited state. And they're asking what is the energy of this electron. And the answer is given which a formula that we are not in a position to prove. And the formula looks like this. The energy of any state in a hydrogen atom is pretty much a function of the principal quantum number. So it is a fixed value 13.6 electron volts with negative algebraic sign divided by the principal quantum number squared. So this pretty accurately describes the energy of an electron in an atom. The negative algebraic sign tells you that the electron is bound to the proton in this atom. You have to spend certain energy in order to free this electron and move it away, far away from the nucleus. So this is the meaning of the minus sign, and it matters, as we're going to discover in a few minutes. Okay, so this is part A. Part B is application of, well, we said that to describe completely the state of an electron in a hydrogen or any atom, you need 4 quantum numbers. And those 4 quantum numbers are principal quantum number, orbital quantum number, they call it, what they call it, magnetic quantum number, or sometimes, okay, so the notation that I used last time, I think the notation also in the textbook is magnetic quantum number, M. I think I used M, which you can check your notes. And the last is the spin quantum number, S. Again, S0, or S. So for our case, you need to know that the range of the orbital quantum number L is a number between 0, 1, and so on, up until the principal quantum number reduced by unity. For my version of the problem, the orbital quantum number can be 0, 1, 2, or 3. And it cannot have any other value. So in this question, they're asking, what is the maximum angular momentum? Which is kind of, well, if you recall, the first semester we defined the angular momentum. How did we define it? We defined the angular momentum as a product of the moment of inertia times angular velocity. That's not a perfect definition, but this is how it works for almost all cases. This was our definition for macroscopic objects moving around. And the orbital, the angular momentum of a macroscopic object can be calculated if you know angular velocity, let's say, around certain axis of rotation, and the moment of inertia with respect to the same axis of rotation. In other words, to tell what is the angular momentum of an electron, you need to know its moments of inertia with respect of axis of rotation, let's say going through the nucleus. And how many revolutions per second or whatever it does, its angular velocity. The problem is that if you know those two numbers and multiply them to get the orbital angular momentum of an electron, you're going to get some meaningless result. And that result is not going to work for anyone. So you may get that the electron is moving faster than the speed of light or some other unphysical answers. So this definition doesn't work for quantum mechanical objects like an electron in a hydrogen atom. The correct answer for an electron in hydrogen atom is that the angular momentum of an electron in a hydrogen atom is given with square root of the orbital quantum number, whatever it happens to be, times orbital quantum numbers increased by 1 times Planck's constant, h bar, divided by 2 pi. So this is a result from quantum mechanics. Here, L can be any of the allowed orbital quantum numbers. For our case, they're asking about the maximum angular momentum, and clearly you're going to get maximum angular momentum if you use the maximum possible value of the orbital quantum number. For my version, we said the maximum value of orbital quantum number is 3. So the angular momentum of the electron is square root of 3 times 4 multiplied by Planck's constant divided by 2 pi. And luckily for you, you don't need to change units for the Planck's constant. They give you the answer in joules times second, which is perfectly fine unit.
So little l, sorry, what does that represent again?
It is orbital quantum number. It's just one number between 0 and the whatever is the principal quantum number reduced by unit.
And so because it's in the excited state, you know that at least for it to be the maximum, it has to be at least 1 below that.
Yep. So the maximum here is 4 minus 1 is 3. The maximum value that this electron can have for its orbital quantum number is 3. This is the maximum value. You had that material in general chemistry, but you probably use different notations. And again, the goal here, in a normal world, we wouldn't even bother to memorize results from quantum mechanics. That's not physics, right? This is not science to memorize something. Usually, Google has all the memory that that anybody may need at any point. But again, it's part of the curriculum. We just have to talk about it. Okay, so this is part B. This is the answer for part B. So answer for part A should be this. Part B is this. What is next? Maximum z component of orbital angular momentum of the angular momentum. Look, the first semester, we didn't even bother to define the angular momentum as a vector. There was a short section marked as optional section, which tells you something how to make the angular momentum a vector. But it is a vector, and therefore it has 3 components. In quantum mechanics, you cannot determine the values of all those 3 components. You are allowed to determine only one of those 3 components. And traditionally, that single component that quantum mechanics allows you to calculate, to determine, to measure is the z component. And the z component of the angular momentum, again, it is given with a formula that we're not in a position to prove. The z component of the angular momentum in terms of units of h bar is any number between, okay. Well, I used different notations, so let's magnetic quantum number m that we talked about last time has value minus L plus 1 and so on up until plus L. In other words, any of the 2L plus 1 values for the magnetic quantum number are allowed. LZ is another notation for the magnetic quantum number. Okay. And therefore, the value for LZ could be, so for our case, we said that the maximum value of L is 3. So the magnetic quantum number is any number between -3, -2, -1, 0, 1, 2, or 3. Any of those 3 numbers. But they're asking us what is the maximum value? And the maximum value is going to be whatever is the maximum value here. So L or Z is the same notation. So those are the same thing. LZ or magnetic quantum number are synonyms. And for us, the maximum value is going to be plus L in units of h bar. So in other words, since the maximum value of the orbital quantum number is 3, this is 3 times h bar. For the maximum allowed value. Again, I feel reluctant to talk more about the state of electrons in hydrogen. The concepts actually are interesting and sometimes surprising results. So any remarks and questions about this? About this homework assignment, this program? So try to finish it tonight, so you finish the next homework assignment on time. And now, look, let me show you something that I wanted to show last time, but we didn't have much time. Okay, let's do first this one. It's quite simple, but we're going to talk about it in a different context. Chapter 31 is dealing with the structure and the properties of atomic nuclei. And the first question that anybody should ask itself is, the first question is, how come that protons, which have the same electric charge, positive electric charge, and according to classical electrodynamics, are going to experience repulsive Coulomb force, how come they stay together, closely packed together in the nucleus, instead of breaking from the nucleus and flying away? So what do you think? Yeah, none of the above is perfectly fine answer in this situation, because all of the other options, some of them are insane, the others are crazy. they don't make much sense. So what happens is that there is another force that we haven't encountered so far, in addition to the gravitational force that we studied, and in addition to the electrodynamic forces and the electrostatic forces that we studied. In addition to those forces, you have a completely new player here, the strong nuclear force. Strong nuclear force is force between the protons, proton and proton, proton and neutron also, neutron and neutron. This is a force between those particles. That force is very short-ranged. It occurs only if two particles get close together to a distance of the order of the size of the atomic nucleus. And within a certain range of distances between the particles, the strong nuclear force is attractive, strongly attractive. Much stronger than the electrostatic Coulomb force between the protons. And as a result, many of the atomic nuclei are completely stable. The protons don't fly apart. Okay, any remarks about this? So keep in mind there are two different nuclear forces: strong nuclear force and weak nuclear force. Right? The names are not very original, but they tell you something. So so far we have encountered gravitational, electromagnetic forces, also second type of forces. In addition to those, we have strong nuclear force, and we have another force that we call weak nuclear force, again, completely different animal. Now, the next question is a trick question. Let's see who is going to be brave enough to answer this question. There are no wrong answers, like I remember in this class.
With the hydrogen atom way more because that doesn't include the weight of the length of a neutron. Or I don't know if there's neutrons in there.
Well, just think about ordinary hydrogen, not deuterium. You don't have any neutrons.
And then both the same.
Yeah, this is what a person that knows classical physics would say. But this is not classical physics. This is a weird stuff. So basically, it is easy to make the argument that the mass of a hydrogen atom is smaller than the mass of a proton and electron separately. In other words, mass of hydrogen atom is less than the mass of a proton and the mass of the electron if they are separate from each other, not bound together in a nucleus. And look, the argument is like this. Let's say that you have a hydrogen atom. Here is the proton, positively charged. Here is the electron, negatively charged. Let's say that this electron is in ground state, principal quantum number 1. how much work, how much energy do you have to spend in order to break this electron free, to ionize this hydrogen atom? Well, the answer is exactly the binding energy. So if you want to take this electron and bring it far away from the nucleus, like here, to be completely free from the proton, you have to spend amount of energy equal to 13.6 electron volts. In other words, the energy of a proton plus the energy of the electron plus 13.6 electron volts. Well, is the energy of a hydrogen atom. Well, not plus but minus actually, because we have to spend this amount of energy. So this is the minus sign in the binding energy that we talked about in a few minutes. But look, this energy, and energy, according to relativity, special relativity, energy is also has equivalence of mass. So this energy of 13.6 electron volts, it is energy, and therefore it is equal to some mass, delta m, multiplied by the speed of light squared. In other words, the energy of 13.6 electron volts that you have to spend to free the electron corresponds to some mass, which is a very tiny mass, because look, electron volt is a very small unit. It is 10 to the negative 19 joules. So very small unit. This is large. So this means delta M, the mass corresponding to this 13.6 electron volts, is very, very small mass. You can never be able to measure it with ordinary tools. So this corresponding mass, the mass corresponding to the binding energy of the electron, is called mass defect. And it has important practical applications. So in other words, when you allow an electron that is far away and the proton to get together and form a hydrogen atom, you can, in the process of bringing them together, the electron emits usually a photon with energy of 13.6 electron volts. In other words, the combined system of proton and electron is less massive than separate electron and proton separate away from each other. In other words, let's say the proton has a mass of 2 kilograms, the electron has a mass of 1 kilogram when they are separate from each other. You bring them together, 1 plus 2 is not equal to 3. It is a little bit less than 3 kilograms. But in a sense, this is important. For example, you can make the argument that in a fuel cell, or even in an ordinary combustion, in a sense, in some distant sense, you are bringing together electrons and nuclei in the process of combustion. When you bring them together, the binding energy is released in a form of heat and light and so on. So it's not completely irrelevant. Now, in chapter 31, we deal not with the atom, but with the atomic nucleus. And you have a very similar situation in the case of atomic nucleus. So here is the nucleus, and it has protons, positively charged, and neutrons that are neutral, but all of them are closely packed together. In other words, those particles, protons and neutrons, are bound together in the nucleus, strongly bound. You have to spend a lot of energy to bring a proton or a neutron away from the rest of the nucleus. That energy is called binding energy. And again, this means that protons separately and neutrons separately, their mass, if they're separate from each other, their total mass is larger than the mass of the nucleus when they are brought together. The difference is, again, what we call mass defect. And it is interesting that the binding energy, the mass defect, for different nuclei is different. And that difference can be roughly expressed in a graph like this. On the horizontal axis, you have the number of protons and neutrons in a nucleus. And on the vertical axis, you have binding energy, energy binding energy, or what we call also mass defect, the same story. You can call it also mass defect. So the most massive nuclei that are relatively stable have total number of protons and neutrons of the order of 250, right? The most massive ones, uranium and so on. And the binding energy for different nuclei follows a curve like this. I'm exaggerating it a little bit, but here it is. Rough, but well, rough shape of the binding energy curve. So look, this means that the most tightly bound nuclei have total number of protons and neutrons of the order of 60, 70. Those correspond to nuclei of iron or close to iron elements. So those are most tightly bound, while nuclei like uranium are less tightly bound, but still bound. If you take uranium or similar nucleus and allow it to break apart and form nuclei that are close to iron or somewhere in the middle of the range, the difference of binding energy right here, this difference, has to be emitted usually in a form of photons or mostly photons. And this is how nuclear fission works. In the case of nuclear fission, you take a massive nucleus like uranium and you create conditions, this uranium nucleus, to break apart into two smaller fragments. The binding energy difference between the fragments, the binding energy of the fragments and the binding energy of the uranium nucleus is emitted. Eventually, it is observed as heat. And you either have one large number of nuclei undergo this transition, you either have a nuclear explosion or you have a controlled nuclear fission process in the reactor. Well, this binding energy curve is an explanation how nuclear power works. And it can give you other ideas. If you start with light nuclei, like hydrogen, deuterium, tritium, if you start with light nuclei, and if you create conditions, those light nuclei to bind together and form heavier and more bound nuclei, the result, the energy emitted is going to be more larger because of the shape of this mass defect energy curve. And this is what you do in hydrogen bomb, right? This is, you have usually deuterium, tritium, or other light hydrogen isotope, even ordinary hydrogen. A nuclear explosion creates high temperature and pressure, which brings together the nuclei of deuterium and tritium, let's say, and you form heavier nucleus with more binding energy. The resulting difference of binding energy is emitted as gamma rays, neutrons, and other. Eventually, they are converted into heat and radiation and light and shock wave of the explosion. And of course, controllable nuclear fusion process happens all the time in the stars. We have sufficient gravitational field, and deep inside the star, the nuclei of hydrogen are close enough so they bind together, form helium. The helium nuclei bind together for carbon, and so on and so forth. It's a chain of reactions. Each of those reactions emits energy, and thanks to that energy, we have sunlight. The sunlight is the energy that is carried with the sunlight is eventually absorbed by animals, plants. They form coal or oil, and so on and so forth. So in a sense, we are all powered by the nuclear fusion in the sun. Just that energy has been accumulated into chemical energy of plants and animals. And when we're burning gasoline, we're using that chemical energy. Okay. Any remarks so far? Any questions? If not, now, what happens when you try to pack too many protons and too many neutrons in a nucleus? What happens is the nucleus becomes unstable. And it spontaneously disintegrates in three different ways of disintegration, and you actually can detect. So if you have, here is one unstable nucleus, way too many protons in it. There are three different ways a nucleus can disintegrate. The first way is called alpha decay. And alpha decay is emission of from the nucleus of helium ions, helium nuclei. So helium-4 nuclei, the helium is proton and proton and neutron packed together. So this is one way that unstable nucleus, heavy nucleus, can disintegrate. Well, an example for this is uranium-234, let's say. So uranium has atomic number of what? What is the atomic number of uranium? 92. Spontaneously, with certain probability, if you wait sufficient amount of time, you can observe spontaneous disintegration of this uranium nucleus to, well, whatever is the element with atomic mass 230 and atomic number 92 plus alpha particle, like this. So this is one possible decay. And of course, in the process, you have energy emitted. This alpha particle is moving fast, a lot of kinetic energy in it. And the energy is carried by this alpha particle. So the alpha particle, again, is helium-4 nucleus. Helium nucleus. This is one avenue of decay. Other nuclei, so this type of decay, well, different nuclei prefer different decay modes. Other nuclei decay via emission, so-called beta decay. And beta decay is emission of electrons. The underlying process of beta decaying nucleus is a neutron in this nucleus spontaneously converting into a proton and electron and a particle that is called electron antineutrino. So very often the daughter proton stays bound in the nucleus. The electron you can observe flying away from the nucleus as so-called beta particle, and you almost never see it. Needs special ways to determine, to figure out, to find, to see the emitted antineutrino.
So the alpha decay, why does 90?
Oh, this should be 90. I'm sorry. Yes, Brandon, thank you. This should be 90. Right? You emit 2 protons with the alpha particle, so you have to conserve the number of protons and the number of. Yeah, thank you. Other comments? And so the final most common way of decay is called gamma decay. And some nuclei prefer to use this gamma decay mode. The gamma decay is emission of a photon. So the nucleus keeps the same number of protons and electrons, but it emits a high energy photon in the gamma part of the electromagnetic spectrum. Now, if you go back to the weak decay, in the case of weak decay, the atomic mass and the atomic number, the atomic mass of the daughter nucleus is going to be the same, but the atomic number is going to increase by 1 unit. Because 1 neutron is converted into a proton. And of course, the electron flies away and the neutrino, antineutrino also flies away, but you cannot see it. And for the case of gamma decay, you don't have a change of the atomic mass or atomic number of the decaying nucleus. Now, one simple way to detect, well, usually gamma or beta particles emitted in radioactive decay is with a Geiger counter. So each beep here corresponds to one particle going through the sensitive volume of this Geiger counter. So next time I'm going to tell you how roughly the Geiger counter works. It is actually not very difficult to explain because the fluorescent lamps on the ceiling work in a similar way. But the beeps that you hear are mostly cosmic rays and natural radioactive decays, mostly from potassium-40 in the walls and around us. However, many everyday objects are quite highly radioactive. So next time you go to Pottery Barn, you have to go with a Geiger counter to select the right object.
Are you radioactive?
Well, everybody has certain amount of radioactivity. We're going to talk about it on Friday. Under normal conditions, that radioactivity is going to be due to potassium-40 or carbon-40. And well, the potassium-40 radioactivity you can see actually, if I have a bunch of bananas here, which have quite a lot of potassium in there, you're going to see that this bunch of bananas is radioactive, beta decay particles. So we're going to continue with this next time. And for the moment, please take a few minutes to finish those end of semester evaluations. Please take those inside after class. Or something because so you probably, Rosa, you probably have to write down the class number, which I don't know.
Okay, yeah, I have it right here.
Okay.
Oh, okay.